For example, today we are going to do the practical number 3, and the aim of our experiment is to study the open circuit characteristics of DC compound generator. And other objective would be to plot the open circuit characteristics of cumulative compound generator and to plot the open circuit characteristics of differential compound generator. So before we move on with our practical, we will cover some of the theories regarding the practical. So what is open circuit characteristics? Open circuit characteristics is a relationship between the field current and the armature voltage at no load condition of a DC compound generator. If you look this graph carefully, whenever the field current increases, there is a corresponding increase in armature voltage, and from a certain point or from point P, the current, no matter how much current we increase, the voltage is going to be saturated. So this is basically the open circuit characteristics of DC compound generator. And if you look closely, this point A is a point where there is no current given to the uh, field winding. At that point, there is a voltage, or voltage will be registered in voltmeter, and this magnitude A of a voltage is due to the residual magnetism. Residual magnetism is uh, residual magnetism is kind of a magnetic a nature acquired by the pole due to the repeated use of a generator. So furthermore, we will look into uh, the types of compound generator. There are two types of compound generator, cumulative and the differential. So as we all know that in compound DC generator, there are both series and shunt generator. There are both series and shunt field winding. So these field winding are wound around a same pole, and in cumulative compound generator, the series winding helps the shunt winding to establish flux. So if you look the direction of a current in both series and a shunt, they are in the same direction. Due to this, the flux produced in a generator would be additive in nature. That means the total flux will be the flux produced by the shunt field and the series field. In differential compound generator, it is contrast to cumulative compound generator. Here, the direction of a current in series field winding is opposite to the direction of a current of shunt field winding. Due to this difference in the direction of a current in respective field windings, there would be a reduction in flux produced in a generator. Uh, if I were to summarize it in form of a formula, that would be total flux would be flux of a shunt minus by flux of a series.
Apparatus required. For DC motor, voltage supply is equal to 220 volt, armature current is equal to 1.8 ampere, power is equal to 300 kilowatt, RPM is equal to 3000 per minute, field current is equal to 0.12 ampere, field voltage is equal to 160 volt, and for DC generator we have voltage supply 220 volt, armature current 1.35 ampere, power is equal to 300 kilowatt, RPM is equal to 3000 per minute, Field current is equal to 0.19 ampere. Field voltage is equal to 200 volt. We need two number of ammeter, two number of voltmeter, tachometer to measure the speed, multimeter, then two number of rheostat, and we need connecting probes as per required. Procedure. Number 1. Collect the required materials. Number 2. Make the circuit as per the circuit diagram as shown in the short shunt cumulative compound generator. Number 3. Verify the circuit connections. Number 4. Start the prime mover and adjust the speed of the motor to the rated speed, that is 3000 rpm. Number 5. Adjust the field of generator so that the generator generates the rated voltage. Number 6. Take the readings of the field current and field voltage. Number 7. For a short shunt differential compound generator, exchange the terminal D1 and D2 of the series field and repeat the same procedure from step number 4. Number 8. For a short shunt cumulative compounded generator, make the connection as per the circuit diagram and repeat the same procedure from step number 4. 9. Plot the graph of field current versus the field voltage for different types of circuits. Now I will go with the precautions. Number 1. Measuring instrument or apparatus should be selected according to the ratings. Number 2. Circuit connection should be neat, right and tight. Number 3. Verify the circuit connection before supplying the power. Number 4. Give a rated power supply. Number 5. The speed of the generator should maintain constant throughout the experiment. Number 6. The field current should not exceed beyond its rating. Number 7. Avoid the contact of naked wires.
So this is our experimental setup. We have a generator here and we have a motor here. So this motor is usually used as a prime mover so that we can move the armature of a generator. And we have a few instruments that is required for constructing a proper working circuit. And these devices, this supply, these measuring devices, voltmeter, ammeter, and this rheostat are usually chosen by reading the rated parameter of this motor. So we have a rated parameter in terms of voltage, 220 volt. That means we have to give the maximum voltage to this motor, that is 220 volt, and that 220 volt is given by this DC supply, power supply module. This DC supply, we just give the DC supply in terms of percentage. So in order to know the actual voltage given, we use this voltmeter in the supply side. And we have this another voltmeter. This voltmeter is used to detect the terminal voltage, and we have this ammeter. This ammeter will use to detect the current in field winding. And here we have a rheostat. This rheostat we will use to vary or maintain the rated speed of the motor so that the same speed will be given to the generator. And we have a couple of jumping wires. This wire will use to connect all the devices for a proper working. So now we will proceed to the actual practical. We have made our connection as per the circuit diagram, and we also verified it. Now we are going to do the connection tracing. First of all, we would do it in two ways, two steps. First of all, we will see the connection at motor side, then we are going to see the connection at the generator side. So first of all, we have given the supply to this motor side A1, then we have given it to motor side A2 now. From this L plus and L1. Then what did we do? Then we short circuited A1 and E2. Then we have connected this rheostat from A2 to one of the terminals of this rheostat, and other terminals it is connected to E2. So this resistor we will use to control the speed of this motor. Then we have to see the connection at the generator side as well. So what did we do? First of all, we shorted the A1 and D1. Then uh, then from A2 we have given it to one of the terminals of rheostat. From rheostat we have given it to the ammeter, and ammeter goes to E1. And this E2 and D1 are shorted. For the output terminal voltage reading, we have a voltmeter here, and this voltmeter we have connected the voltmeter from D2 to positive side of the voltmeter terminal, and the negative side of a voltmeter terminal goes to the A2. Now we are going to give the supply here, and we will give the rated speed to the motor, and we will vary the field current. First of all, this rheostat is at maximum position so that the field winding current is 0, and slowly we will decrease the resistance and increase the field winding current, and that increase in field winding current will give us the voltage reading at terminal side. So that is basically what we are going to do. For this experiment we will obtain 2 or 3 data, and we will show you.
Now we will give the power supply. We give the power supply, that is 220. Now we will check the RPM and we give the power supply to 220, and now we are going to check the RPM.
So we are going to maintain the rated speed of this motor. So rated speed is 3000 rpms. So in order to maintain this 3000 rpms, we are going to change the resistance of this rheostat. Now we have given the supply, and we have kept the rheostat at the maximum, so that the current flowing to the field winding will be minimum or 0. So that at that time we have the residual voltage, that is 5 volts. So we are going to take the subsequent reading by reducing this rheostat, and we are going to take the reading at the interval of 20 milliampere. We are going to take the interval of 20 milliampere, and we will take the reading till 180 milliampere.
Now we are going to take the first 2 initial readings. So when the field current is 0, then we have voltage equal to 5. Now we are going to vary the field current to 20 amperes.
Kecil.
got reading 47.
So this is our last reading. So we have given the current, that is 180 milliampere, which is the rated field current of this generator. And for that reading, we have got 200, approximately 230 volt of terminal voltage. For this second part, we have exchanged the D1 and D2 connection. We just interchanged it, and we are going to keep the setup everything same, and going to follow the same procedure and see the terminal voltage when we change the field current. Now we have done our practical, and we are going to present our observation table. So this is our first observation table, and this is for cumulative compound generator. And the second table has the readings, which is basically for differential compound generator. After collecting this data, we have plotted a graph to see the relationship between the cumulative and the differential DC compound generator. So as you can see, the cumulative is a bit higher than the differential compound generator. So this curvature usually represent the open circuit characteristics, and these individual graphs will help us to determine whether that particular DC motor or DC generator we used in our practical is a cumulative or differential. Thank you.